question regarding the lecture yesterday? So what I'd like to do today is spend the first 5 minutes or so to review what we learned yesterday, and then discuss more about possible solutions. So yesterday we saw one solution, which is the hard wavelet, very simple solution. So here we have introduced additional solution. Okay, and given those solutions, how to find, given all the choices of half band filter, how to factorize or how to choose the appropriate choice of H0 and F0. Okay? So yesterday we discussed the properties and definition of downsampling, of upsampling, of decimation, so the cascade of a filter, and downsample for decimation. Now, who remember why do we need a filter before downsampling? Because of aliasing, right? So we need before downsampling. We want small or no aliasing, then we have to have a filter, which is a band pass, a low pass filter, band limited to pi with 2, right? In this case. So here is decimation, here is interpolation. So who remember why do we need a filter after upsampling? So to fill in the zero value. So that depends on what do we use. If we use a low pass filter, then the resulting interpolated signal will be a smooth copy of what we have. If we use a high pass filter, then you have a highly varying signal, and so on. Okay? So for the case of 2-channel, we have two choices of filters: a low pass or a high pass filter. Okay? And one other thing you want to remember is the first branch is basically capture low frequency signal, low frequency component, and the second branch capture high frequency component. If we have application where you don't need to use the second branch, you don't have to. So there's no signal there, for example. Okay, so this way, as you see later on, we'll be able to decompose or divide the signal into different bands. Okay? So one question we ask is that, okay, we can decompose, but can we reconstruct? Right? So the question of how to reconstruct and what kind of error do we have? We know that if this is an ideal filter, then there's no aliasing, no distortion whatsoever. Right? But if we have a practical filter, then we have aliasing here. Okay? So we have aliasing, we have imaging, distortion, and so on and so forth. How do we find these four filters such that the output is a copy of the input, and we allow some delay? Okay? So that's the statement is that how do we find the possible choices of filters such that the output is a copy of the input. Now, there are many ways to solve this, and we see that on today. We look at polyphase representation, where we have another more efficient way to figure out the PR condition. So this is called PR, for perfect reconstruction. But for right now, what we have done yesterday is we take x of n with d cross of x of z. We carry it through the whole system, right? We measure what this is, which is the product x0 and x. Then we're going through the cascade of downsampling and upsampling. And we see that this signal is basically the combination of that one and then with a shifted by pi. Okay? And so on. So after we know of this, we find a condition for FIR solution. And so here's a summary. Basically what you have to do is you have to find a half band filter, P0 of z. Okay? And after we find a half band filter P0 of z, we factorize P0 into F and H. Okay? And when you do that, you're done. Because the other two filters is basically related to H0 and F0, right? So if you look at this, What is f1 of n equal to? I'm sorry, f0. So this is how we relate it in the frequency domain or z domain. What is it in the time domain? Minus 1 to the n h1 of n, right? So we know that if I know h1, if I know f0, I can find h1 and so on. So f0 and h1 are related this way. And then so this one here, f1 of n is minus 1 to the n h0 of n. So f1 and h0 this way. That's how they related. Okay? Alright. And we also show that L is an odd integer, right? Okay? So yesterday we have one example of what would be P0, a half band filter. And the easiest one that we have yesterday is P0 is 1/2 1 plus z inverse square, right? So in the time domain, this P0 will be basically at 1. So this is 1 plus 2 z inverse plus z inverse z minus 2. So you have at 1 is 1, and then 1/2 at 0, and 1/2 at 2, and 0 elsewhere. That's how the impulse response P0 of n look like. Is this a half band filter? Yes. Because it is 1, right, on an odd integer. We need it here. So here's L. If L is 1 in this case, and then 2 points away from it. So in this case, minus 1 and 3 is 0 and so on. So this is one of the very simple, right, half band filters. So suppose this is your choice of your half band filters. Then what could be the factorization? Well, to do that, we have to find, again, this is FAR solution. So you have to find all the 0 of P0. Then allocate the 0 to either F0 or H0. Okay, so there are many ways of doing this. So let's go to them. F0 of Z, F0, H0. Okay, so here is the z-plane plot, the pole 0 plot for P0. Here is pole 0 plot for F0 and H0. So what are the 0 for P0 of Z? Minus 1. So that to find 0, remember that we need to find where this function goes to 0, right? So as z equals minus 1, so this is 1, this is minus 1. So we have 2 0, it's a double 0, and minus 1. That's it. Okay? So we have 3 choices, right? But the normal, the fair way of allocate is 0. It's 1 for each. Okay? The other choices are not very useful. So here I can allocate 1 to F0, 1 to H0. So in the Z domain, P0 of Z is 1/2 1 plus Z inverse square equals 0. Right? The product of these two. So each of them look exactly the same, right? This one was 0, 2, 1 plus Z inverse. That's F0. Another one is 1 over 2, 1 plus Z inverse. That's for H0. So for this special case, okay, they are exactly the same. So basically, this is where we stopped yesterday, right? Are there any questions on what we have so far? Can you tell me the property of this system? Oh, we have none. Is FIR? What else? Is it low pass or high pass?
Low pass.
Low pass, right? Because it has a 0 at pi. If you plot it out, you see that it is a constant at 1 at the DC. Okay, it's a low pass system. Is it symmetric? Is it linear phase? So this example, the factorization gives you a linear phase solution. Okay? Linear phase meaning that the impulse response, or if you compute a phase of this, what is the phase of this system?
Omega over 2.
Omega over 2 minus omega over 2, right? It's called the system. So the phase, you have a positive group relay, a negative slope. Okay? So this is linear phase. You can show later on that this is also orthogonal. So we'll show that the basis function for this system is orthogonal. If we use this kind of filters in a wavelet sense, the basis function that associated with the particular factorization will give you an orthogonal, right? So we know how to recognize linear phase. It's very easy, right? Linear phase, basically you're looking at to see whether the impulse response have a center of symmetry or not. So if I plot the impulse response f naught of n, you see that there are two exactly the same values, right? So we have one was square root of 2 at 0, and the same value at 1. So from here, I can see linear phase. I can see that there's a center of symmetry at 1/2. So that's my phase, okay? So this is, my phase is minus 1/2 omega. So that's how you recognize whether a system has linear phase or not. So whether they have a center of symmetry. And that particular index, where the center of symmetry is, that's the slope of your phase response. Okay? Alright, so to recognize linear phase, it's easy. To recognize orthogonal, what you have to show is whether f naught and whether f naught of z is h naught or z inverse. I'm going to add in so for this case, the order is only 1, right? Order 1, so this is z minus 1. I want to see whether the impulse response of this system and this system are flipped. So take a look at this equation. Tell me, how do I write this in the time domain? How does f naught of n related to h naught of n?
Minus 1 plus n minus 1.
N minus 1? Minus of that. So what was it? Give me your final answer.
F naught of n equals minus.
Let's take a look at this. Who know how to take inverse Z transform of this form?
It's not
Into two steps, right? It's a product. Z inverse times this. And both of them are LTI system. You know, the operation, you can look at it. Right? So what is f h naught Z inverse look like? In inverse Z transform. You flip the impulse response, right? You take h naught of n, if you replace z with z inverse, what happens? You flip this one, right? So the time index n, it was from 0 to 1, now from 0 to minus 1. Because changing the power of z is basically changing the index. Okay? So basically you take the h naught, we flip, and then you delay. So basically you have 1 minus n. So you're right. You have minus of n minus 1. Okay? So that's correct. Okay? So another way to test is that I want to plot the two impulse response of my solution. Okay? So let's plot the other one. H naught of n It's going to be like this, exactly the same, right? Is this system and this one satisfy this? So again, if I take H0, if I flip it and shift, is it the same as this? Sure. Okay, so in this example, right, you have, they both symmetric and orthogonal. So that's how you check for orthogonal. Later on, we'll show that this is the only system, only simple system that is both orthogonal and linear phase. Okay? So, any questions here? Alright. So I'm going to give you more example. Okay, so this is a longer length system. Okay, so let's look at a more complicated example. Okay. Z equal to C0 is 1/16 minus 1, 0, 9, 16, 9, 0. This is my notation to give you the coefficient of the impulse response. If you plot this out, right, you see that the center of symmetry at what index? This is 0. What's the index for center of symmetry? No, not 16. The index. The value of 16 over 16 is 1. It's 3, right? So it's 0, 1, 2, 3. Okay, so at L equal to 3, you have 1. And then you have a symmetry system, right? Because you can see that, you know, if I fold this side over here, it's exactly the same. So we have a 9 over 16, and then 0, and then minus 1 over 16. So this is 0, 1, 2, 3, 4, 5. It is a valid half band filter for our solution. So how do I check whether it's valid or not? What do we need to check? Whether L is odd or not, L is odd here, and whether at the second point of wavelet is exactly 0, which is the case here. Okay, so this is a valid solution for the product filters. And it turns out that if I factorize this, P0 of Z equal to 1 over 16, 1 for Z inverse, the fourth power, 1 minus 4, Z inverse, Z inverse. Okay? So if you using this impulse response, find the Z transform, right, and find all the zero, you see that there are 4 0 and minus 1, and there's a pair of zeros on the real axis. So what we'll do next is we're going to take this choice of P0 of Z and talk about possible solution. Okay, so I'm going to do exactly the same as this, but now we have more choices because we have more zero to work with, right? How many zeros do we have? 6. But all the 6 have 6 zeros. Okay, there are 4 zeros at pi, and there are 2 zeros elsewhere. If there are 6 zeros, there are many choices you can allocate. So I can give 3 and 3, and so on. Okay, so let's look at various choices for this particular example. So here's P0. Yeah.
I think that the least minus we call 1 over 60. Minus.
Oh yeah. So this is minus sign. Okay. You can put a minus in here. If you want. Okay. P0, F0, and H0. Okay. So let's see. So where are the zeros for P0? There are how many zeros? 5 minus 1? 4. 4. So there are 4 zeros minus 1. And where the other 0? Okay. So if I look at this, the Z transform right here. Okay? We see that the coefficient is real coefficient, right? So I have to have, how many choices do I have? If this is a real coefficient polynomial, how many choices of 0 do I have? I have 2 zeros, right? Can it be arbitrary 0? Can it be here and here? No, why? Why not? It has to be complex conjugate. Right? That's one choice, okay? So it has to be here and there. That's one choice. Where's the other choice? They're real, okay? That's one choice. The other choice is here on the real facets, right? So which choice do I have here?
Second.
Why? Suppose you don't do, this b minus square root. If you don't find that exact value, how do I know that it is on the real axis?
Because it has green solution.
It
has green solution. One more.
Suppose you don't find a solution. If you find a solution, you can plot it, right? If I don't find a solution, okay, how do I know that the choice is here?
It's outside. Because we aspirated that.
No, don't look at that. I don't want you to know to find a solution. Intuition. How do I know that the choice is this but not that? Why? You accept that the 2 0 will be the real value, right? So it's on here. If this is C, some value. C is the solution for that, okay? Where is that? What is that? 1 over C. Why? Okay, good. The product of two roots is 1. That's one way to see it. That's the other way to see it. Let's make use of the fact that this is what? It is, if you look at the phase of that function, what is that phase? Phase is minus omega, right? So this is linear phase. What do I know about 0 of linear phase system? This, you can learn about that. What is the 0 for linear phase system? It has to be inverse each other, right? For linear phase system, you can show that if Z0 is a 0, Z0 inverse also a 0. 0 come in pairs. Okay? Because you can flip this, right? If we flip that, then you can show that the inverse also in the solution. Okay? So if it's C inverse has to be a solution. Okay? So we know that there are 4 0 pi and a pair of 0 on the real axis, and the magnitude is basically inverse of each other. Is that okay? So let's discuss how do we distribute or divide this 6 0 into F0 and H0. And let's distribute them such that you have orthogonal. So the first choice here, give me a orthogonal solution. And then we have linear phase later on, okay? So second choice here, we linear phase, and okay, we'll use other phrases later on, okay? So how do I distribute the 0 of P0 to F and H such that I have orthogonal solution. Inverse. Okay? So if you choose a 0, let's say C over there, to F naught, then C inverse have to be in H naught. Okay? Because they related as the inverse. Right? If you plug Z1 in here and set out with a 0, then Z1 inverse will also be the location of H naught. Right? So it means that if I assign this first 0 to F naught, if I want to maintain orthogonality, where is the other 0 have to go to? To H naught, right? Let me go over here. How about 0 at 4, at 5?
Which one? It's
H1 have 2. Why is it? H1 have 2. Because if you look at this, right? How suppose F naught has 10 zeros. How many zeros does H naught have? 10. Exactly the same order. Okay? So and then if you plug in Z equals minus 1. Also minus 1 here, right? Minus 1 is own inverse. Okay? So it means that, and there are 4 to distribute. They have to be equal. Okay? So they have 2 and 2. And for this example, this is one example, right? And what is the other choice? The other choice is, you can swap this. But that's just redundancy. So if we don't care about redundancy, this is the only orthogonal solution for this particular factorization. Right? Because this 4 zeros will be 2 and 2, and this pair have to be distributed. C here and C inverse there. That's the only solution for orthogonality in this case. Yes? Okay, so orthogonality, one of the ways to check is that whether F naught in a time domain is a flip of H naught. Okay? In Z domain, it means that if there's a 0 at Z1, the inverse 0 has to be in H naught. Okay? So that's basically tells us how to distribute the 0 P naught. Right? If I choose a 0 F naught here, let's say C, then C inverse we have to go to H naught. Okay? So it means that well, as I said, tomorrow we will discuss why this is the case. Okay? Yeah.
This equation, the order of two equations, because here we have F1, and then for H1 we have this minus 1.
Yeah, so
it's order of two.
right. So this example, right, order is 1. So this is 1. In the other example, what is this power have to be? In this example, what is F naught of Z has to be equal to? What is that power? Should be the order, right? Should be 3. And the reason why I have this 3 is to make sure that the system is causal. If I don't care about causality, then I don't care about this delay. Because basically this is flipped, right? I have to shift by the maximum order. Otherwise I don't have causality. In order book, they don't really care about causality. So they don't have this Z to the minus. It turns out that this is L, okay? So you can remember that the power of the order here is basically your center of symmetry of P naught. So L goes to here, L is 1, this is 1, so. Okay, so that is our first factorization, which yields orthogonality. Okay, let's discuss linear phase. Now, why do we care about orthogonality or linear phase? It will become clear in a Maxflat exercise. Orthogonality is very good for noise reduction, so on and so forth. If you have white noise, if you have noise, then you would use orthogonality in the application. If you have image and video to process, okay, where phase is very important, then you want to use linear phase solution. So depending on what is the application, you would choose different choices of system to analyze. Okay? So I'm going to discuss now the factorization of P naught into F naught and H naught such that each of them is linear phase. Is this linear phase? Is P naught linear phase? Yeah. Look at the uniform response. It's symmetric. Right? So tell me how to do it. What do I do with this C inverse system? Can I put C here? And C inverse here? Why? Why not? It will not be symmetric, right? Because symmetric means that pair of zero have to go together. Okay? So if I assign C here, then its inverse has to be in the same Z plane. Right? So they have to go together. So that takes care of this pair. How do I distribute 4? 4, 0, minus 1. Okay? What are the choices? 2, 0 here, okay? 2, 0 there. What are the other choices?
And the other 0.
Can I erase this? Right? So red color is linear phase, okay? So again, I need C and C inverse, right?
This 4 and 0.
1,
No,
3,
yeah, no 0. Yeah.
well, 3, 1, okay?
4.
Yeah, so you see that the way to distribute this is 4, 0 high. You have many different choices, like 2, 2, or 3, 1, or 4, 0. Right? But basically that's what you do. So the important thing is this pair goes together. Is 0 at pi give you linear phase? It's a system with 3, 0 at pi. This is linear phase, right? Is that give you linear phase?
No.
Let me erase more and need more stuff, okay? You can deduct it, okay? So this is C inverse, that 2, 0, and pi. How do I test to say a system have linear phase or not if I'm only given the pole zero plot? I don't want to compute the Z transform and so on and so forth, too complicated. How do I just look at it and say it is linear phase? Well, you see that this can be factorized into two systems, right? A product of these two systems, right? If FIR system polynomial, I can factorize it this way, with LTI, right? Do this have linear phase? Yeah. This have linear phase? Yes. Why? No, I see.
Because
Why the symmetry? I
2, 0 in state.
okay. So to get symmetry, I have to plot. I have to find the impulse response, right? I don't want to do that. I'm just saying that looking at it, How do you recognize it? Right? So this only tells me where the location of the zeros are. Let's go back to here and check. Here are how the zeros are related. Right? So saying that -1 is a 0, -1 is not a 0. So -1, system with 0, -1 or 1 is always linear phase. Because -1 is its own inverse. Right? And 1 is its own inverse. So any system with 0 at 1 or -1 is always linear phase. If this is linear phase, if this is linear phase, it's a product linear phase. Sure, because phase add. Right? You add two linear, you got linear. Okay, so basically you only have to check to see whether this pair go together or not. You don't really care to check the 0 at -1. It's always give you a linear phase system. Is that okay? Okay. So we see that you have two choices, right? The other choice would be 4, 0, which is not a good factorization. Okay? And in fact, there are names for these particular choices. Okay? Let me give you the name. So this one, you look at this, the coefficient is 1, 2, 1. I'm ignoring the factor outside here. Okay? I'm just giving you the coefficient of your impulse response. It's 1, 2, 1, right? Because this is 1 plus the inverse square. So it's 1, 2, 1. This one is -1, 2, 6, 2, -1. Okay? This is 1, 1, right? That's 1 plus the inverse. This guy is -1, 1, 8, 8, 1, -1. This choice is called 3-5 system. If you read image compression literature in Wavelet, they refer to a 3-5 system. That's the 3-5 system, which is a system where they have length 3 and length 5 for the filters. Okay, this is the 2-6 system, right? Length 2, length 6. In fact, if later on where Professor Jack discussed about JPEG 2000, who have heard of JPEG before? I'm sure you know JPEG, right? JPEG 2000 based on Wavelet. Okay, so when we discuss JPEG 2000 application of Wavelet, you can see that one of the choice is a 3-5 system. And this is actually used in a standard based compression. The nice thing about this system is it's all integer values. Now integer is very good. Why integer is good?
Easy to compose.
It's very easy to compute, right? Because if you think about it, your image is an integer or floating point. If you take a look at an image, how many bits is in an image? 8 bits, right? It's a grayscale from 0 to 55. It's 8 bits. It's an integer format coming in. And the transformation that you use to analyze, if it's integer, it's very, very nice because you don't have to use a floating point processor. Okay? And it's also allowing you to have lossless compression because this particular transformation does not lose, you don't have to forget anything. Right? So it's allowed for lossless compression. It's very, very fast because all you have to do is integer-based, computation. Now, however, it doesn't. It's about 0.5 dB, slightly worse than the best choice. Okay, so I'm going to discuss another choice where it is used. It's called 97 wavelet. Okay, but basically this is the choice that people use in JPEG 2000. This is also a very good choice. It is used in Ricoh. Ricoh is the camera maker and the printer. They have their own compression engine, and they actually use this particular 2.6. index compression. It's worked pretty well also. Okay, it's very, very fast, all integer based algorithm, and it's also lossless. Now losses is important in medical imaging, because when you compress medical image, you don't want to lose anything based on liability or losses and so on. Okay, so also good for manipulation, because you don't want to lose any information when you manipulate the images. For compression, it's also okay. So, any question regarding this? Destroy?
I have questions.
Yeah.
You just said that when you compute F0 and F0, we must maintain the orthogonal.
That's one choice. One choice, right?
Okay.
You have many choices. You can have orthogonality, or you can have symmetry. Or I have another example where it doesn't have to be any of this. Okay? So tell me, how do I distribute this? Here's another example. This is F0, P0, F0, H0. Okay? So use the same one here, C inverse, 4, 0, I. How do I distribute the 0 so that it's not orthogonal, it's not symmetric? So here we discuss, right, orthogonal, factorization, and symmetric. I want none of this.
Now here we distribute
So tell me how to distribute C and C inverse. Separately. Okay. So let's C here and C inverse here.
two one or 3 1 or
3, 1. Okay. Good. Is this linear phase?
no.
Why not? You need pair of 0, right? For this C. So this is obviously not linear phase. Is this orthogonal?
No.
No. What's the fastest way to check if it's not orthogonal or not?
It's the order of F not
Very good. They have to have the same order, right? You said that the order is exactly the same. And not the same order, right? This is order 2, that's order of 4. Okay? And this is not useful in application. So you see that, there are all the choices that you can factor, and it's not useful. Okay? Alright. So let me give one more example, and then we go on to the next topic, okay? On how to distribute this load. F0. Okay? This example P0 is 8, 0, and minus 1. There are 6 zeros elsewhere. There are 2 zeros here, and there are 4 zeros there. It's not important right now exactly where it is 0. And I know that P0 is linear phase. What is the order of P0? 40. That's the number of zeros that we have, right? You have 6 plus 8 is 14. Okay? And we know that okay, this is linear phase. These are pairs, right? Where are the other pairs? Are these 4 related in any sense? They have to be, right? If this is Z0, where's Z0 inverse? Is it here, here, or here? Is it 1, 2, or 3?
1, 3.
Now here, right? Because Z0 inverse have invert phase. You flip the phase, you want to flip the radius, right? So inside go outside, and the phase flips. So this pair go together, and this pair go together. And the fact that they are complex conjugate also tell us that it's linear phase and real coefficient. Right? Because real coefficient means that this and this have to go together as complex conjugate pairs. And this go together as conjugate pair. So it's not only linear phase, but it has real coefficient also. And any question on that? Linear phase because there are 3 pairs of inverted zeros. It's 1, here is 2, and here is 3. Real coefficient because the zero either on the real axis or are complex conjugate pairs. Right? The real axis, pairs, pairs. Okay? Alright. So if I want orthogonal, how many choice do I have for orthogonality? Give me one way to do it. How do I deal with 8, 0 here? 4 and 4. I know that I have to distribute them equally. Okay? How do I deal with this 6, 0? If I put 1, this guy here, where this one go? In the other side, right? How about this pair?
One inside.
One inside, one is outside. Okay? What do I do with this pair? One inside, one outside. This kind of distribution guarantees that for every 0, Z0 in here, Z1 in here, the inverse in the other side. That's what we need. Okay? Z1, 0 in here, Z1 inverse. The inverse in the other side. What does the coefficient look like? Is it real coefficient?
Yes.
Or complex?
Real.
Real coefficient because the zeros is either real value or complex conjugate pairs. Okay? Is it the only way to get a orthogonal system? No. Tell me another way to factorize it and still keep orthogonality, and they're different. What do I do here? Still the same, right? So I have no freedom on assigning 0 to pi. It has to be 4 and 4. How about this choice? What if I keep this 2, right? And move this one outside. Okay? I don't want to be 2 outside, move 1 inside. So here again, I keep linear phase, real coefficient also, right? I mean, not orthogonal. Still also real coefficient. Right? Is that clear? What are all the choices? Any other choice? Will not give you real coefficient. Right? So I can choose this, and the one outside, right? It can be erased here. That's one way. And the inverse can go to the other side. Right? So it be, one out here. What do I do? Would this work? No. That be okay? If this is Z1, where's Z1 inverse? Down here?
Yes.
Oh, this is not good. It has to be in a different place, right? So let's do it slowly. Okay? Let's do it one by one. So this is Z1, where's Z1 inverse go? out here. Right? Because Z1 and Z1 inverse have to be in different factor, different choices, right? Different filters. Okay? How about this guy here? This out here, right? And then I can choose this and that. No. Yes? Wait. I can choose this one. What do I choose? This one. Okay. So that's another choice. It is orthogonal. How about real coefficient? No. There is no pair, compressed conjugate pair, right? It's orthogonal only. And so on. So as you see that, as we have more and more zero, you have more and more choices of orthogonal system. You know, before you have only one, right? In only two examples. Now you have many, many. Okay? So let's discuss the trade-off between these two choices of orthogonal. Because they're useful in the sense that they're orthogonal and real coefficient. Right? We want real coefficient because most of our input are real coefficient. Okay? So what are the trade-off between the two different factorization, as you can see? What are the difference between them? How do I name them? You know, how do I say, you know, a certain name? You know that you pick one of them. So you have to somehow say the difference between these two, right?
You want to go first up circle, after that down circle, but in the other you go first down circle, then you up circle.
Okay, so that way into the analysis. I'm just saying that if you look at this right now, only, how do I make a difference? How do I? Okay, so the way to see whether it's different or not is to see the magnitude and phase of a system, right? And you know that's how you characterize a system. What's the magnitude response? What a phase response? Okay? So compare F naught only. Tell me the magnitude response with two. Are they the same, are they different or not? So who think they're different? Different magnitude response. Why? Who think they have the same? None. So one win. I'm not. Why are they different?
0, 1, 0.
So what he says is that the only difference between these two systems, F naught prime, is 0 is flipped outside.
The F not about is stable.
Stable. There are no pole in this system. It's always stable and cold. Okay? So let's think about this, right? What happened when you flipped 1, 0 to the other side? Do they have same response, same magnitude or not?
The magnitude is the same. Only the phase is shift.
Okay. You can show that. I'm not going to show it here because if I take about 10 minutes to show it, you have to use all pass factorization and so on and so forth. But a property of linear system is that you can flip a 0 out. Flipping meaning that keep the same phase, same angle to change the radius. It turns out that they have exactly the same magnitude. Okay? Respond exactly the same with some scaling factor. So what I'm saying here is that the two have exactly the same magnitude. You plot them, and they don't care about the scaling factor. They're exactly the same. Okay? I'm not sure whether you know this, but you should know that. You take DSP before? So you should know that, okay? If I flip a 0 outside, keeping the same angle, but invert the radius, then exactly the same magnitude response with some scaling factor. And the way we show that is by using the all-pass properties of system properties, okay? Okay, so keep that in mind. The only thing that they can different is the phase response, right? System that 0 inside have smaller phase, minimum phase. And you can also show that using all-pass. Who have heard of all-pass system before? All-pass? No? All-pass. No? All-pass, the system have magnitude 1, okay? Phase are different. In any case, this is a minimum phase. This is maximum phase. In the sense that the phase here have a lower lag than the phase here. Okay? So in this minimum phase, the other choice, H naught, we have maximum phase. Because all the 0 are flipped. Right? So you have minimum, flip to maximum. And so on. So this is maximum phase, this is minimum phase. Right? So that's what happens. Okay? So the choice in the weather toolbox that you will use this afternoon, this is called D4. For double sheet is the person who derived all the properties and the factorization here. Okay? Double sheet, enriched double sheet. 4 is for number of 0 and pi. So to D4 meaning that you have a minimum phase, D4. Because 0 inside the unit circle. So when I say minimum phase, is that I'm looking at all systems have the same order, order 7, have same magnitude response. This one has the smallest phase lag. Okay, that's what it means. It means that among all systems, the FIR system with 7 zeros, okay, 4 here, and the 3 here. I have the same magnitude response. So I'm allowing to flip this in and out. Right? This one has smallest phase lag. That's what it means. You can show it. You can show that it's a long proof. You can show that if I flip the 0 outside, the phase will increase. Again, using all-pass properties. Again, linear phase solution is important because you want in image and video, phase alignment is very important. An edge, right? If you have out of phase, you see ghosting artifact. So when you want to use transformation, that is linear phase. That's why all the wavelet using the compression at linear phase. The DCT, the discrete cosine transform using JPAC, is also linear phase, and so on and so forth. Yeah? So now the phase is very important for image and video, because you can see if it's the hour phase, you can see the ghosting artifact. So here, linear phase solution. Again, F naught, H naught. Okay? Now, many different solutions. We'll discuss a few. Okay. So how do I deal with this pair? Gonna go together. Right. So how about the other? I want linear phase and let's say real coefficient. Okay. Both linear phase and real coefficient. How do I deal with this? This set of 4 zeros. Do they have to go together or not? Together. Right? When linear phase, then this pair go together. If you want real coefficient, then this pair go together. If you want both, all 4 have to go together. Okay? Let's use the other side. Otherwise, it will be not fair, right? So that's one way to distribute 0 as not at -1. Okay? And here we can put 4 and 4. Alright, that's one way. This is called the 9-7 wavelet. 9 order 8, 8 zeros, 9, length 9, right? Order 6, length 7. This is the 9-7, this is used in JPEG 2000. This is the best in terms of compression, the best wavelet to use in terms of how good it is, and also how in terms of implementation also. Of course, you go to a higher order system, you have higher signal to noise ratio, but the complexities might be too big. So this is a good trade-off between length and complexity, okay, and also PSNR. Another choice is I can have 2 here. The other set there. I can have 3 and 5. Right? And so on. So you see that the other choices basically is how I distribute the 0 and pi. Right? And so on. 9-7 is a length. Right. The 8 zeros, 8 zeros order 8, and you have a constant length 9. Okay? So in this particular factorization, the only one that you need for linear space, you need to remember the 9-7 JPEG 2000 factorization. Okay? And there are many ways to factorize this. There are both linear space and real coefficient. But basically, you have to distribute the 0 to pi. So let me pause for question. And any question regarding different ways to factorize, how do I factorize, and so on. Is that clear? Okay. Let's talk about half band filters. Okay, I need help. How do I start? How do I start? Yeah.
I think you should start with one linear phase on orthogonal window.
So you want to narrow down the scope of the design. That's good. So let's design linear phase, half band filter with real coefficient. Good. How do we start that? How do I? Yeah, that's symmetric. How do I find it? How do I characterize a half band filter? How do I know that it's a half band filter?
This have only one only.
You can look at the impulse response, right? It's 1, and then every 2 points go to 0. That's one way to do it. Okay, so you can say that, okay, what do I know about half band filter? I know that there's a center of symmetry, L, right? L's R is 1, and I don't really care what this is, but an L minus 2, and L plus 2, the one exactly 0, right? The next point, I don't care what this is, and then an L minus 4, L plus 4, and so on. That's one way to do it. But that's hard to do, right? I have to figure out how to choose this location. How do we design our filters? Forget about half band. how do I design low pass filter? This is low pass half band, right? How would you design low pass filters using MATLAB? What does a low pass filter look like, right? You want to find somehow, this is omega. You want to say in a range from 0 to omega p, which is the pass band. I want it to be approximately 1, right? And I want omega s 2 pi approximately 0. I want a method to somewhat, approximate or find its coefficient. And then when I plot it, plotting p naught of e to the j omega, I have an approximation. Right? I have something like this, and then like that, right? With magnitude, so like that. Okay? So there are many ways to design this, right? Raman or empirical is one way to do it. What you have to do is you have to figure out what is the length, what are omega p, omega s, what's the weighting between the deviation. I want, this is 1 plus delta p, this is delta s. I want to see what is delta p over delta s. And that is your design parameters that you use to fit into Raman's, right? I'm sure you heard of Raman's algorithm, which is empirical design. That's MATLAB. You can say help Raman, you can see what's going on. What they want is what is omega p, what's omega s, what's the length, and what is the weighting. Okay? And that's how we're going to do it. We're going to say that we're going to figure out what could be the length of a half band filter. Symmetric, real coefficient. Can this omega p, omega s be arbitrary? Or is there any special properties that this is going to have? How is weighting? Okay, so the question to you is intuition. Can this be arbitrary? Can I choose 0.1 pi and 0.7 pi? Why not? Somebody say no. Why not? Intuition. Why do you think that this cannot be arbitrary?
Quality of the filter. It
Yes.
is depend on the quality of the filter.
The quality.
If the rank is too large,
Okay. Like, what if I have, 1,000, 0.4 pi, 0.6 pi, and 0.4 pi, 0.5 pi? Would that be okay? Would length and the length 0.4, 0.5. Would that be okay? Think about this. You see that what you are given here, what is given back will be the impulse response and approximate that ideal response. Right? That's what happens, okay? There's a lot of constraint on this particular one. It's not arbitrary. In fact, the design of freedom is half of the order. Right? If this is, let's say this is 7, right? That's 6, 5, 4, 3, 2, 1, 0, and so on. Okay? This is too big. Let me do 5. Okay? It's 5, 4, 3, 2, 1, 0. What is the length of this? This is 5. That's 6, 7, 8, 9, 10. Right? Length 11. Okay? Given length 11, if this is unconstrained, there's no way I'm going to get 0 here, 0 there, 0 there, and 1 there. Right? My design freedom is half only. Half in the sense that I have no freedom on this one, right? And exactly 0. Okay? I have no freedom over this, and so on. So, in fact, they have to be related. I cannot choose some arbitrary. And so on here. Okay, so the point I'm going to make is we want to find the condition on omega p, omega s, and its weighting. such that we guarantee to have 0, 0, 0, and so on and so forth. If you choose some arbitrary, there's no way to enforce this 0. Is that clear? So your design freedom is limited by a factor of 2 because you don't have the whole design freedom here. You have half the design freedom because the other one is 0. Okay? So I'm looking for frequency response, right? So I'm going to work with frequency over here. Okay? So how does P naught of Z related? So I know that P naught of Z minus Z is 2Z to the minus L. Remember, this is one of the PR conditions that we derived a lot of yesterday, right? And we deduct that P naught is a half band filter. You can show that if P naught satisfies this condition, then that is a solution. We derived that yesterday. Okay? I want to start from this property, look at the Fourier transform, and figure out how omega P and omega S are related. That's how we do it. Design meaning that start from frequency response, right? Constraint, and find P naught of N. So we have to start with frequency. Okay? So frequency is Z. So I have P naught of e to the j omega minus P naught of e to the okay. So this is a shift in frequency. Right? This is 2 e to the minus j omega L. What's next? So how do we use linear phase? Linear phase implies what? What is P naught of e to the j omega? If it's linear phase, how can I write this? There'll be a phase term, right? And there'll be an amplitude response term. Is that clear? Right. Linear phase is symmetric. I can factor out half the phase. Factor out the phase, right? And then what's left is sum of both sides. You need to remember how to do this, right? How do I find the phase response and the amplitude response of this system? If you look at this, what do I see? I see that if I factor out this L omega, what is left is a constant. Basically, I'm shifting this back to 0. Right? Factor out phase is shifting this response back to 0. Right? It's equivalent. Right? Is that clear? So what I see here is if I shift this back to 0, what do I get? A constant. This gives me what? E to the minus j omega, e to the plus j omega. What does that give me? 2 cosine. Yes, cosine, 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 so on and so forth. Okay? So you see that the phase response is exactly the center of symmetry. What is left is sum of cosine. Right? I'm going to call that, for shorthand notation, P of omega. Or P omega as sum of cosine. Right? It's basically 1 plus 2 times this, cosine omega, 0, 2 times this, cosine 3 omega, and so on and so forth. And the index for omega is basically the distance from the center of symmetry, right? And you have 0 omega, 1 omega, 2 omega, 3 omega, and so on and so forth. At the end, you have L omega, because you have 0 to L. Is that clear? I'm grouping all of that into an expression they call P of omega. Now it's only a function of omega. This is basically no phase in here, right? Okay? It's a real quantity. And this is a direct property of linear phase system. Is that clear? So what I'm going to do next is I'm going to take this and plug into this, right? So far, this is arbitrary. We constrain this on this. Okay? Let's take a short break. When you continue, we'll take this form and plug into here and see what happens to P. Use this property of linear phase system, linear phase filter in the half band properties, right? Remember that one is linear phase property. We're going to constrain this form by substituting this into here. Okay? So we say P naught of e to the j omega will copy this form. Right? So we have from here we get e to the minus j L omega P of omega. Right? That's P naught of e to the j omega. Okay? And we have minus. How do I find the form for P naught of e to the j omega minus pi? What do I need to do? I need to substitute omega minus pi into this form, right? So basically, whatever I say omega, we're going to substitute omega with a shift in omega, okay? So I see I will have e to the minus j L and then omega minus pi, e of omega minus pi, okay? E to the minus j L omega minus pi, p of omega minus pi equal to 2 e to the minus j L omega. So far, it's okay? All I'm doing here is substituting, the linear phase form into half band condition. And let's simplify, okay? I see that in this side I have e to the minus j L omega, e to the minus j L omega, e to the minus j L omega. Okay? So I'm going to take them out, cancel them out, okay? What is left? What is left is P of omega. This is e to the minus j L omega, which is out. And I have e to the plus j L pi. What is that?
Cos L is also
Okay, so L is R. E to the j L omega pi will be minus 1. Right? Minus 1 give you plus sign. Okay, so I have plus E omega minus pi equal to 2. So here I'm using the property that L is R. Okay, so basically this is telling us how the amplitude response have to be related. So we see that P of omega and the shift have to add to a constant. So let's think about this, right? Let's say P of omega is something like this, okay? This is 0 to 0.4 pi. This is some arbitrary thing, okay? This is pi. So we have P, and we have H. That's it, this is P of omega. How do I plot P of omega minus pi? Let me move this one up. This is P of omega. How do I plot P of omega minus pi? You shift by pi. Okay, so we would have this, which is real. It's going to be like that, right? We shift to pi. We would have that, so on. This is P of omega minus pi. The sum has to be a constant for all frequency. This is a very strong condition for all frequency. One frequency is easy, right? all frequency is very, very, very hard to do because omega is infinite. Number of omega is infinite. Right? I mean, omega is 0 to 2 pi. You take any irrational number. It can be 0.4578, whatever. Okay? So, would this work? With this particular choice, is it valid for this equation? No. You will have, a constant, and then 0 here, and so on. So what does it have to do? Have to be overlapping, right? So I have to bring this to here. Okay? So basically, this will not work. I'm going to erase this and bring them in, right? It has to be overlapping because otherwise you have a 0 here. How much overlap do we need? Right? If this is 0, what do I need here? A constant, 2. This is 2, right? If this is 2, what do I get here? 0. Like that. Right? Otherwise, there's no way to get a constant. And I see that a straight line give me a straight line. The sum of two straight lines be a straight line. All you have to do is figure out the endpoint. So you're going to have a constant, and a constant. Alright, right? Is that clear? So what is the condition on these two quantities? They cannot be arbitrary. Right? Now tell me what is that distance? Because I know that distance is the same as this distance, right? What is that distance? Pi minus omega t. It's right here. Right? It's that guy shifted to there. Right? So you have pi subtract omega t. Omega t. Okay? So it's saying here that this is pi. No, sorry. This distance is omega t. Sorry, thank you. This is pi minus omega t. Is that right? Okay, good, thanks. Okay, so we say that omega s has to be equal to pi minus omega t. So conditions are omega s equal to pi minus omega p, or omega p is omega s equal to pi. So if 0.4 is the pass band cut off, and 0.6 is the region. So this is 0.3, 0.7, and so on and so forth. They have to be symmetric around pi over 2. Right? And this is why you call half band, because the symmetric point is at pi over 2. So half of the bandwidth, right? 0 to pi is your bandwidth, maximum frequency. Symmetric is at half. That's why we call it half band. The half band occupied try to approximate half the total frequency. When you have third band, fourth band, and so on and so forth, you generalize this to pi over 4, pi over 3, and so on and so forth. And half band meaning that the pass band is at half frequency. Okay. So now we know how these are related. How about omega p, omega s? Can it be arbitrary? Of course not, right? Because this is again a very strong condition. If you have a peak here, like that, now the filter, right? What do you need over here? Can this such that it will be like this? No. And then exactly the flip, right? So it had to be the opposite, and so on. So that deviation and this deviation is exactly the same, right? So you have to have omega p equal to omega f. Again, very, very constrained design algorithm. So in MATLAB, what you can do is, you can say P equal to Rama's, right? And here is the order. Order here is 2L, right? L is here. Order is 2L. Let's say 2L. Pick L equal to 5, that would be 10. Okay? Have you used MATLAB with this before? So what's the next step you have to do? You have to give the beginning and the end of each of the band. Here you have two bands, pass band and stop band. And the start and the stop frequency of this band will be 0, this and that, right? So an example would be 0, 0.4. It's saying that the start of a pass band will be at 0 frequency and the stop at 0.4. And the next two numbers will be for the next band, 0.6, because of this. This is basically equal to pi, okay? 0.4 pi, 0.6 pi, and then pi will be 1. Right? When MATLAB see this, vector is 4, it knows that it has two bands. The next step is we're given the value of this band, right? So it will be 1, 1, 0, 0. That's the ideal response. 1, 1, 0, 0. So this is saying that the first one is a pass band, approximately 1. Well, I can put 2, okay? Because this is 2. It doesn't matter, it's a scaling factor. You can put 2. You just scale by 2. You can put 1 and 0 and 2, okay? And then that's it. If you don't say anything about the weight, then it will assign equal weight. Simple. So you should try, go to MATLAB today, and then choose 10 and so on. Design this, take P, plot it out. You see that it should be 1 and be 0, and 1. Have any questions here? So let me summarize, okay? So far we discussed perfect construction, FAR solution. We discussed how to factorize the half-band filters into F0 and P0 and H0 to give us orthogonal, linear phase, real coefficient, and so on and so forth. Right? One thing left is how to design half-band filters. So we start with the fact that any half-band filter will have this property when L is R for our example, for our design, right? And then we want to constrain on linear phase and real coefficient because we know how to design linear phase and real coefficient. Right? You can use Raman's algorithm, you can use many different algorithms in MATLAB. Designing non-linear phase, complex coefficient is very, very hard. Okay? So we're better off constrain our design freedom to a class or filter that has been done before, which is linear phase and real coefficient. Linear phase and real coefficient, for this example, we see that it will be a linear phase, there's a phase term, and there's a real quantity term. This is sum of cosine. Okay? So if we plug this into here and use the fact that L is R, the response, the amplitude response will have these properties, which means that omega P and omega S have the same distance from pi to 2. Right, so this distance and that distance is exactly the same. And you can see that here, right? Okay. I can take half of pi and take pi to 2 minus omega P. Equal to omega S minus pi to 2. I can do that. So what is pi over 2 minus omega P? It's right here. Right? What is omega S minus pi over 2? It's right there. So another way to remember is that they sum up to pi, or the edge is symmetric around equal distance around pi over 2. And therefore we have the term half band. Okay? So we show that the sum has to be high and also a peak. The maximum has to be corresponding to a minimum. Right? And therefore deviation has to be the same. And therefore we have the same weight. Very important in identity. The first one dealing with how to interchange operations of filter and downsampling. You can show that if you have a cascade of L by M, G of Z to the M, this is the same as L by M. You can prove it. And I'm not going to discuss it, but you can prove it yourself. Okay? And you see that this is LTI, this is linear but time invariant. You cannot interchange operation. But for this special case, you can. So you interchange them, Z to the M becomes this. Okay? The second one, F by L, Z to the L, same as Z. Again, in general, I cannot interchange operation. In this case, where this is a function of Z to the L, you can show that it is equivalent to this form. The third one is I have a cascade of M downsampling, L upsampling, equivalent to upsampling, downsampling. Greater common denominator in other words, M and L are relatively prime. You know what that means, right? So 3 and 4, okay. 2 and 4 is not. Right? This is the greater common denominator factor. Is that clear? So in general, you cannot interchange this operation because they are not LTI system. However, if they are relatively prime, if M is 3, L is 4, okay, they are relatively prime, then you can interchange operation. You can prove this also. Okay, I'm leaving all this exercise for you to prove. Yes, assuming that we know this, we want to discuss polyphase. We will come back to you this many, many times. So I'm going to leave it, right here for now. I'm not going to be raised, okay? Let's discuss polyphase. Okay, so let's discuss why we need this. Let's look at decimation. I have H, I have down by 2. Let's think about what is involved in this process. You've seen this before, right? This is in all 2 branches in the filter bank. The first, filtering and downsample. Filtering because you don't want aliasing, right? Is it efficient to do it this way? Is that a good way to build the systems? Who think this is a good way to implement or build the system? Are there any other alternatives that's more efficient, lower the cost? So let's think about it. I'm going to filtering, do convolution, and then what do I do here? Throw away every other coefficient, right? I keep 1, I throw away 1. I keep 1, throw away 1, so on. That's very, very wasteful. It's not good. I don't want to do filtering and then throw away information. It's not good, right? Is that clear? I don't want to, is there a way I can move this block to this side? I want to throw away information first before I do filtering. Because throw away information have no cost. Right? In computing, it's basically an indexing. Right? You go to the next index. Just skipping index. There's no cost there. Okay? If I can move this block to this side, then the filtering operation will be half the rate at the rate lower rate. Okay? So polyphase representation it basically allows us to efficiently representing this. Okay? I want to somehow move this block to this side to have an efficient way to implement this operation. Is that clear? Okay. So how do we, so what is polyphase representation, right? I want to derive it in the Fourier transform as the transform domain and also in the time domain. They are corresponding. Okay? All I'm doing now is taking the string of number and then divide it into two different bands. Okay? So you take a whole bunch of of ball, and you keep one to this ball, one to this, and so on. Just divide them differently. Okay? What I'm going to do is I'm going to divide it into H even and H odd. So what goes into H even will be H odd 0. Assume causal for now. Okay? H2, H4, and so on. All the even index transform. What goes to H odd? H1, H3, H5, and so on. That's a unique representation, right? Given any string of number that have index 0 to infinity, right? I can always divide it into two different strings. One of them will be have even index, one is odd index. Vice versa, if you're given two of the strings, how do I get back this? If I have, H even, H odd, what do I do?
Insert 0.
You have to do this, right? Insert 0, and then interlace them, right? Like that. Okay? So that's how you do it. So, okay? So let's think about it.
Insert 0 half even then plus 2 half odd.
Okay, so if I given H even and H odd, tell me what's going on here to give me H of n coming out.
We do upsample H even and
Upsample them by 2. That's the operation of inserting 0, right? Because the spacing here is not the same as spacing there. Right? This is one spacing here equal to 2 spacing there. Right? Relatively speaking. Okay? So you have to upsample, and how do we shift? What do I shift? This one or this one? This or this one. So I'm doing this. So I see that I'm using the upsampling block and delay to actually figure out how to reconstruct. Okay, so I can actually talk about this interlacing, right? From the process, describing in the process of upsampling and delay. And it's very clear from here. How about in Z domain? What is the equivalent in Z domain? What is x of z equal to? Have to be depend on H even and H odd, right? What go in here?
That's follow to
The square
Yes.
And this is also z square?
No.
No?
No square.
Not square? Z?
2D. We contain two times the frequency.
2 here?
Now.
That is z square, right? And what do I do here?
Z minus 1.
It's right there, right? This x even. Upsample, what is that? No. Remember upsampling in z? In omega it becomes 2 omega. Z becomes z square. Okay? X even of z. Upsampling becomes x even of z square. X odd of z. Upsampling becomes x odd of z square. So x of z. X even of z square plus z inverse odd of z square. So this is a direct copy of what we draw here, but in z domain. That's it. That's polyphase. Very simple. It's a process of distributing into even and odd. Okay? Now in terms of representation, I'm going to represent this as follows. In the system point of view, okay? If I have x of z, input x, output y. I'm going to draw x of z in this form. What do I have? I see that two paths, right? One is x even of z square. One is z inverse h r of z square and f again. So this whole thing here is x of z. Same input, same output. Alright? X of z. X of z becomes h even of z square plus z inverse is odd of z square. So this is in terms of signal representation. This is system representation. Okay? So I'm going to go here. So what do we see? I see it's a down swing by 2, right? So here is down by 2. It's down by 2. Right? Filtering, down by 2. Filtering, down by 2. Polyphase, representation, down by 2. All these three are equivalent. Now, using this form, I can see that at the first noble identity. What do I see? If this is 2, if this is z square, I can interchange operation. Do I have it there? Yes. Now by 2, z square, z square. I can move this block through here. That becomes z. I can move this block in here. Right? I cannot pass the inverse. So that's a function of z squared. So basically I'm going to redraw this after moving this block to this side using the first noble identity. Okay, so I'm going to erase this part right here and write the equivalent structure using the first noble identity. Okay, so I have, so moving this block to this side, right? I have now by 2, z inverse, now by 2, h even of z now, okay? H r of z and are there any questions so far? From here to here, is using the first identity. Okay? So let's call this number 1, number 2, number 3. Right? Let's compare the cost right now. Suppose H have order 10. Order 9, 10. An example. Okay? For every output here, how many multiplication do I need to compute the convolution? Think of this. This have 10 coefficients inside here. How many multiplications do I need for each output coefficient? 10, right? Because what you do is you flip, multiply, and shift multiply. So for every convolution point that you want to have here, you need to do 10. So we have 10 multiplication per unit input. Okay? So there are 10 multiplication for every input point, unit time. You have 10 multiplication. Okay? And you have 9 add. But that's add is cheap, okay? Multiplication is more expensive. Look at this form here. What is how many coefficients in each element? 5. You are taking 10 numbers, right? You distribute to 5 and 5. So each of this have 5 coefficients. Is that clear? How do you have to do it for every time? Or is it different? So let's see what happened over here, right? So to figure out whether you have to do it every time or not. To figure out what's going on with input X and going to the block. So tell me the operation. What do we have there? What happened when a string of number going through this? So let's look at cause, okay? When X of 0 goes through this branch or that branch? Top branch, right? X of 0. And then at that time, this is 0, right? X1 come in. Where does X1 go? Does it go down here or up here? Down here. Because this delay. Okay? So X1 go there. Where does X2 go? Up. X3, X4, X5, and so on. Again, what is that? That is serial to parallel buffer, right? Basically, you just block the input. You just form a string number going in, just form a vector, right? And there's no cost there. We never implement downsampling as it is. We implement it as just blocking, right? A string of number coming in, you just block it to get a vector representation. Okay? So when do we have to do this operation? Do we have to do it every time it's coming in here? Or we do it every other time, every 2 times? 2 times, right? Because it takes 2 unit time to form a vector. Right? You have x0, 0, and x2, x2, x0, 2x1, and so on. It is 2 times. So this operation, 5 multiplication per 2 unit time. Okay? This one, same. 5 multiplication per 2 unit time. Combine, what do you get? 5 multiplication per unit time. It's half. That's what we want. We want somehow not to waste the computation. We don't want to compute and throw away information. We want to do it just right. In other words, saving a factor of 2. Right? Instead of doing 10 multiply and then throw away the other 5. Well, doing a vector processing right now, right? To get 5 per unit time. Okay? So right now, polyphase is what we use in modulation. So if you open up a JPEG encoder or wavelet encoder, we never implemented like this. You see polyphase in there. Okay? You see there's a blocking to go from 0 to parallel, and you see there's a parallel multiplication. Always the case in the chips or in the software that they sell. Okay? Any questions here? Is that clear? So let me start the question.
What is phase in this?
Phase?
Yes.
Well, you don't really care about the phase, they're equivalent. Right? Because what you see here is the axis here, y is there. This is a unique representation. Equivalent and unique. These have the same axis y coming out. Oh, polyphase. Poly is many. Okay? Many phase. You can show that. Okay, you can show that if you take a phase here, you can actually split down to the 2 different phases. Okay? If you're interested, I can send you papers on the properties of phase. Basically, poly is many. You have one phase to split down to several different phases. Okay? So let me, alright. Can I erase this? Okay. The next thing I'm going to do is, so this is in the analysis, right? In the synthesis, you have the opposite, right? You have a filter by upsampling and filter, F0. Again, this is not efficient to implement. Why? Because you increase the rate and you filter. Even the 0 in there, but you still have to increase the rate. So this filter has to operate at high rate. Right? It's not good. You want to move this upsampling to this side. Similar to, you want to move this downsampling to the other side. So in this case, I want to use a second noble entity to move this block to this side. I'm going to skip all the operations. The result is going to be like this. So the steps are taking F0 and writing this form. F even, F off. Okay? So what you have will be as F. You have F even of Z, R of Z up by 2 and okay, from here to here involve polyphase and the second analytic. And leave that exercise to you. So first, what you have to do is writing F in the polyphase form, which is look like this. Okay, F with the F even, Z square, the Z inverse, and R of Z square. And then we use the second double identity to switch the operation. Okay, again. This has 10 multiplier, and you do 10 multiplier per unit time, right? But here, you see that this is 5, 5. All you're doing here, you're doing at low rate. Right? So this is 10, the unit time here is twice the rate. So this is twice the rate. And then you have to do, or only do it at the original rate, and then you interlace them. This process what we have discussed over here, right? It's erased. Basically, take the two signal, we interpolate, right? We upsampling, and then interlace them like. So that's just parallel to serial conversion. And you never do it like this. It basically pick out the vector to serial, right? You only basically pick out the operation. This is the opposite of this, right? This is serial to parallel. This is parallel to serial. Okay, here we block the input into vector. Here we deblock. Go from vector back to a string of numbers, sequence. Okay? From 8 to the minus 5. That's my Z transfer. Okay? Let's see how to find the even polyphase and the odd polyphase. Look at this form, what do I have? What did it say here? All the even power of Z go to this guy. All the odd power of Z go to here. Right? Because that will be even, Z inverse is odd. So I'm going to take this Z transform. I will have two groups. The first group will be even power of Z only. Second group, only odd power of Z. I factor out Z inverse to get that form. Okay? You need to help me. Where are power of Z here that's even? One. Only one of them, right? How about the odd one? The factor out Z inverse. What is that? 2, and 7, Z to the minus 2, and 8, Z to the minus 4. So as it is now, I have the polyphase form, right? Yeah. Even of Z square, Z inverse is out of Z square. So tell me what is H even of Z? 1. Just 1. What is H odd of Z? 2 plus 7 Z inverse. Right, because this is Z squared. 8 Z to the minus 2. That's how we do it. This is H odd of Z squared. X odd of Z. Suppose this is what I'm going to do in the analysis. How do I reconstruct? What's the filter here? What is X naught? X naught is 1, right? Remember filter bank, we have H naught, H1, right? X naught is 1, H1 is 1. Z inverse. Okay? 1 Z inverse. So this is very simple system. Okay? Just 1 into there. How do I reconstruct? Of course, you can do, half band and so on and so forth. Let's not do that. Let's think about exactly what's going on here. What is that? Parallel, a serial to parallel, right? How do I cut back the signal? So just interlace. So you take this up by 2, up by 2. Is that right? This is actually this is Z. Z inverse. that right? So yeah. So let's take x0 here, x1, x2 coming here, right? Over there will be x0, x2, here will be 0, x1, x3, so on. What is that? x0, 0, x2, 0, here, 0, 0, x1, 0, x3, 0. No, I need to delay the other way. Right? Okay. Right? If I do this, then I have x of n minus 1. If you see that this system here is very, very simple. You get perfect reconstruction. Okay? The filter here are 1, Z inverse. Z inverse 1. It's not very useful, but it is PR. Okay? This is called lazy filter bank. It doesn't do anything, right? It is actually a perfect reconstruction filter bank. What is the input coming in? That delayed by one sample. Okay? You will see the polyphase look like this. So let me just for it. Okay? Are there any questions regarding PR now? It is PR, right? What if I insert something in the middle? Okay, so here's how I do it. I do exactly the same form. I want to insert in the middle a block. And this block is identity. Then it doesn't change anything, right? Okay? Instead of one block, I'm going to have two blocks. One block here, another block here. If this block are invert of each other, then it's still okay. Right? So I can choose U and U inverse. Where U is an arbitrary 2x2 matrix, real coefficient. This product is identity, and therefore this system exactly the same as this system, right? In the input-output sense, and therefore this is still PR. This is a PR system, right? In particular, what if I use 1, 1, 1 minus 1? What's the invert of that matrix? 1 over square root of 2, okay? Put 1 over square root of 2. What is that invert? 1, 1, 1 minus 1?
One minus one minus one.
One is square root of 2, right? This time this, 2. This time that is 0. This time that is 0. This time this is 2. This is orthogonal. This is orthogonal matrix. Transpose to be the inverse. Right? That's easy way to see it. Anyway, have you seen this before? Have we seen a system with 1 and minus 1 before? That's a hard wavelet. Let's think about it, okay? I want to move this block this side now. Move this block that side. I want to show you that this is the polyphase representation of the hard wavelet that you have discussed before. Okay? So I'm going to do the reverse way. Going from here to there. Okay? So this is a constant, it doesn't matter. Z to J, right? So this block will come first. Well, I'm going to have a block here with 1, 1, 1 minus 1. The inverse down by 2, down by 2. This guy on the other side, okay? One, 1, 1 minus 1, and square root of 2 somewhere, right? Okay? Okay. This is for reference only. This is the conventional way to draw a two-channel filter bank. You have seen this many times, right? We split into 2 branches, we combine them. Okay? This is a new way, polyphase way of looking at the same thing. Okay? This is the polyphase form. This is the equivalent of the polyphase form. Because this is a constant, when you move it, doesn't go from 0 to the m, right? It's a constant, stay constant. So tell me, what is h naught of z, h1 of z for this system? How do I find h naught of z? Here, the transfer function from input to the first downsampling. What is it? What is that transfer function? 1 over square root of 2 and what?
1 minus the last
1 plus
e power
z
power square.
How do I see that? So I want to erase this and draw this in the branches, okay? What does 1, 1 means? It means that this path is 1 and this branch is 1. Right? Okay? You have a matrix 1, 1 times vector, right? A and B. A and B is right here. A and B. What do I see? I see that 1 times A, 1 times B. So 1 times A, 1 times B. Okay? So when I draw a matrix, like that, you have to visualize that in a signal form. It's going to be like this. Right? And 1 minus 1 is 1. In a signal form, what do I get? 1. This is minus 1. Okay? That's signal form. Is that clear? So from here it's very clear, right? The transfer function from input to the first downsampler is 1. Forget about it. It's square root of 2, okay? It's 1. The inverse 1. How about the second branch? What's H1? H1 is from input to the second downsampling. What is that? 1, right? Minus Z inverse. That's what we see in our wavelet, right? It's an average and difference operation. How about F naught? F naught, right, is from here to there. I'm going to erase this again and drawing this, right? So 1. Okay. What is F naught of Z? And F1 of Z. F1 is square root of 2. So what is the shuffle function from upsampler to the output? One. Right? So it's still 1 plus Z inverse. How about F1? From here to there. That's a minus 1 and plus Z inverse. Okay, so minus 1 plus Z inverse. And we know that R is both linear phase and orthogonal. H naught and F naught are exactly the same, right? And linear phase is symmetric. And they have a 0 at minus 1, 0 at minus 1. It's also orthogonal. What is P naught equal to? How do I find P naught? How do I check to see whether this is PR? One of the check is the P naught is a half band filter, right? With R, L, we're done. Right? So what is P naught? It's H naught times F naught. Right? To be 1/2 1 plus Z inverse square. And that is half band. And we start today with this example. Okay? So we become full circle today. Right? We start with an example, we decompose to get this form. And then we use polyphase representation as a simple example first. And then we recognize that as long as the middle block in cascade is identical, it doesn't matter what I put in here. Right? It's still PR. In particular, if I choose this block to be a 2-point DFT, you can see this as 2-point DFT, okay? There is 1, 1, 1 minus 1. It's a 2-point FFT, right? Like this. And moving this to the other side, I can show that the corresponding filter will also be a higher wavelet. Okay? So that could be at the end of today's lecture. Basically, we learned about factorization, right? We learned about polyphase representation for efficient implementation. We also use polyphase to show that it is easy to construct, right? So there are many ways to choose these choices. We change this block and keep them to be invert each other. You have all the choices here. They might not be useful. Next time we will continue, we will cascade more blocking here and have longer system. Right? As long as you cascade, you can take the inverse. You're done. So structurally, you're enforcing the PR condition by choosing the polyphase representation of the analysis and synthesis to be the inverse of each other. As long as they inverse each other, you're always guaranteed to be PR. So that's another way to represent VFPR system by choosing a block in the middle to be inverse of each other. And here's one example. Okay? So that's the end to it. What's next? Từ khoa chừng 11 giờ hỏi câu hỏi đi ha. Question. System analogy. So what are the applications of wavelet filter bank, right? So my plan for the course is on Monday when we continue, I will use the projector. I will show you what I will talk about wavelet. So far we have not discussed wavelet, right? So you have no idea what wavelet means, okay? I'll show image and what are the wavelet representations of the image and why is it important. And then we'll discuss what are applications. So you can talk about adaptive filters, you can talk about noise reduction and so on and so forth. Okay? So Monday we'll show some images and show the resulting of applying a wavelet transform for images and how is it useful and important. Okay? And then we'll look at the trade-off between different systems. So you apply a hard wavelet and look at the result. And we're applying a 97, which is the one that JPEG 2000 used, and see the result. And see what, why do we use one over the other. Okay? And then on Tuesday, I'll show you an image compression toolbox. So a friend of mine at Wisconsin, he designed a very nice toolbox for PC, and it's be available in the lab also. And there you can actually pick an image and then apply JPEG, look at compression, and then use the same bit rate, okay? And apply wavelet and see what are the trade-offs. And you can see that JPEG have blocking artifact, right? And wavelet have bringing artifact. And we'll discuss, what are the trade-offs between different set of wavelets and so forth. So the next 2 days, you'll see how this applies. Just bear with me for until then. I know this is, hard to see what is used for, but this is setting the fundamental for the theory. Okay? And the trade-off more generally depends on the application, right? When they design JPEG, they say, okay, can I use block 8 by 8, or can I use 16 by 16, or 12 by 12, and so on and so forth. So there's a whole study of designing different transform, DCT transform, for all of this. And it turns out that this block is good because back in the 1980s when they designed JPEG, the highest resolution you have is set, right? This is 352 by 288. That's the size of the image. And that size of the image, 8 by 8, 16 blocks work pretty well. Have the most correlation for compression. Okay? But this is too expensive because back then in the 1980s, a megabyte of RAM is very, very expensive. Okay? A computer have 32 meg or 64 meg. Right? That's a PS2 computer. Okay? So it's very expensive to use a big block because a big block requires more memories in the cache, right? Because the speed of computation is not only in how many multipliers, but how big the block is, right? If you load in a block, if the block is too big, you miss the size of your cache. If you go outside the cache and then bring it in, that operation is much slower compared to the speed, right? Okay, so the way that you're choosing the block size depends only on the cache size. So they say that for this size with a 32 kilobyte cache back there, 8 by 8 works pretty well. So we use 8 by 8.